All right, 13.4. Feels like it's been a while since we've jumped back into some new material. We're going to continue talking about areas, but now we're going to be specifically talking about surface areas. Surface area means the area on the outer side, if you will, of a three-dimensional object. So this is the number of square units needed to cover a three-dimensional surface. Sometimes you'll hear things referred to as lateral area. The lateral area is the sum of the lateral faces of a prism. So surface area is for all three-dimensional objects. Lateral area only applies to prisms. And we're looking at the faces around the sides of it. So you have all of these rectangle pieces that are coming down. Those are the lateral faces. And then the bottom and the top are considered the bases. So if you were to take the actual surface area, it would be the sum of those lateral area pieces, right, all those lateral faces, and the area of the bases, top and bottom. Specifically, we're going to look at some specific shapes. We can talk about a cube. This is the shape of a cube in a three-dimensional form, and then the one on the right-hand side is a net. And a net is if you were to imagine that this cube were actually a box and you cut along the edges and then you laid it flat, all the edges flat, you'd get the net. It's not necessarily the only net you could get for that particular object, but it's one possible net you could get if you cut it in a specific way. So if you'll count for me, you've got six faces, right? 4 around the edge, and then you've got the top and the bottom. And in a cube, they're all the same, right? They're all squares. And what is the area of each square face in a cube? Yes, it's S squared. I think I probably need to do something. Maybe I'll do red for right now, so we can see it on both backdrops. So each of those faces are S squared, right? Each one of them. And how many did we say there were? There were 6. So there are 6 times S squared, or S squared added together 6 times would be our surface area for our cube. And you can think about it as well, if you prefer, from over here, the net perspective, right? Each of these faces is one of the faces in the cube over here, and they all have an area of S squared, and so you can see it from a two-dimensional perspective if you lay it all flat in a net. Okay, so we're going to change our object slightly, or at least make it more of a broad statement. We're going to look at the surface area of a right prism. Okay, so if you'll remember, right means that it's straight up and down. There's no angle to it. So we're not talking Leaning Tower Pisa here where things are at a slant. It is straight up and down. It's the way most structures are built, right? 90-degree angle kind of stuff. If B is the area of the prism's base, whatever that base is, and P is the perimeter of the base, H is the height of the prism, what we're going to find is the formula for the surface area of a right prism. So we have 2 bases. So our surface area would be to add the 2 bases together, top and bottom. And then what you'll notice is that we have a bunch of rectangles because we're working with prisms, right? The rectangles, however many, I didn't mean an equal sign, I meant a plus there. However many rectangles there are, we're calling that n numbers of rectangles. We will have the length times the width of the rectangle. Well, the height, if you will, of the rectangle, actually let me leave off the n for the moment. I'll get back to that in a second. The height of the rectangle is h. That's what they told us in our description. And then we have the individual sides. So in this object down here, I have 5 of them. In general, we don't know how many we're going to have. So we would have S1 plus h times S2 plus ... however many sides times the height. But if you'll notice in this equation, they all have h's in them, right? After I get the 2 bases there, everything has an h in it. So another way of writing this is to take your base And well, it's 2 times my base. Let me write that down since I already have the base plus base written. And to sort of factor out my height. So if I factor out my height, I'm running out of space. What I'll have is I'll have S1 plus S2, all of these. Does that make sense? You just pluck the H out of each one of them. Okay, so whatever the H is, it's 5. Instead of adding the 5 or multiplying the 5 all these times, you just multiply it to the sum at the end. But this right here is exactly what they told you up here. If I add together all of those S1 to S whatever, however many I have, in this figure I have S1 to S5, I get the perimeter of the base. So instead of writing it in this form, a condensed version is to take 2 times my base, and remember that capital base means the area of the base, plus H, which is my height, times the perimeter of the base. Okay, so just as a reminder, this B stands for the area of the base, and the P stands for the perimeter of the base. And of course, H is the height of my pyramid. Okay, so far so good. So you might be thinking, do I have to memorize all these formulas? And of course the answer has to be no, because I give you note cards. But you should have some kind of an idea of what's being used for what in order to make sure that as you're looking at an object or asked a question about it, you can identify which formula you're supposed to be using. And I also would like for you to recognize that these formulas are not just sort of appearing out of the middle of nowhere. They come from doing some basic arithmetic facts on stuff you already know, right? Areas of rectangles. It's length times width. So we can create this equation if we're careful enough to see where all the pieces are coming from. So let's do some examples. Have an example. It wants us to find the formula for the surface area of a right rectangular prism. Now, it is a formula we're creating, right? But as you're taking a look at this, we could do the same problem with numbers in here if we were asked to. We could do it from scratch. So there are how many faces here? 6, but some of them duplicate themselves, right? Like the front of the box, the one that's sort of poking out at you, is the same as the back of the box. Right? If you imagine a shoebox, this is sort of the picture you have in mind. The left-hand side and the right-hand side, they're the same size, and the top and the bottom are the same size. We're duplicating some of these. So there's no reason to find each one of them individually if we recognize that we have these duplicates going on. So my surface area is 2 times the, and I'm just going to write it this way for the moment, the front plus 2 times the left and 2 times the top. So obviously I could have written bottom in place of top, right in front of instead of left, or back instead of front. But these are sort of the pairing up of the matching sides. So let's actually looking at these dimensions that it gives us for the front. It's a rectangle. L is one of the dimensions. What's the other one? Height. The height, H. So the area of this rectangle on the front is actually what? LH. Yeah, 2 times LH, and we don't really need it in parentheses. The left-hand side or the right-hand side, actually the right-hand side is the one that's easier to see where the markings are. What's the area of the box on the right-hand side? Yeah, it's WH. And what's the top's dimensions? And that's my equation for surface area of that particular shape. So if you encounter this shape again, and they give you actual, like numerical values instead of L, W, and H, you have a couple options. You could use the formula we just created. That would be fine. Or you could just calculate all 6 of those areas, really 3 of those areas, and add them together directly from thinking about the rectangles themselves. Your choice. All right, so that was prisms. Let's shift a little slightly to the area of, or the surface area, excuse me, of a cylinder. So if you can imagine, we have this cylinder that's drawn three-dimensionally on the left-hand side. And if we had like a roll of toilet paper, this would be really actually simple to do, right? You could take one wrap around of the roll of toilet paper and you could cut it. And you could lay that toilet paper piece flat. And then the parts we wouldn't have, of course, is the circle on top and the circle on bottom in terms of flat pieces. It's actually the net over there on the right. That is the net if you were to lay that all flat. So what you notice then is that you have two distinctly different types of pieces here. You have circles on top and bottom, and then you have a rectangle in the middle. You know the formulas for areas of circles and rectangles. So if you're looking at this from the purpose of the rectangle, the area, of course, is length times width, and we'll put the dimensions there in a moment. And then your area for a circle is what? Pi r squared, and we have two of them, right? So these are the pieces that we're sort of combining together, but we want to do it from the perspective of having these particular lengths and widths and so forth. Our circles are actually already given because the radius is already still in terms of r. So my two circles, my surface area, is 2 times the formula for a circle, pi r squared, right? Pi r squared plus pi r squared would be 2 pi r squared. My rectangle in the middle, I have to work a little bit more at. What are the length and width of the rectangle that they're showing you there? Yeah, it's 2 pi r and h. So clearly that's the length and that's the width that I'm multiplying together. Let's actually take a look real quick at where that 2 pi r comes from. Clearly the h comes from the picture just fine. I think you can see that one okay. Why in the world is there a 2 pi r? And where have you seen 2 pi r show up before? You remember? Somebody said what? It's not area. It's the perimeter of a circle, or we sometimes call it the circumference. This is what you get. The circumference equation is 2 pi r. Right? If I go all the way around my circle, that's 2 pi r. And so it makes sense that this long sheet, if you will, on the net, right, the rectangle part, is the perimeter of the circle. Right? That's if I cut down the side, that's exactly what would be laying flat, is all the way around the circle. So that's where those pieces are coming from for my surface area for my cylinder. I thought I had an example, and we do. So let's do an example of this one with a soup can. A soup can has diameter of 2 5/8 inches and a height of 4 inches. So we have diameter here, we have a height here. What is the total area of paper needed for the can's label if the label is to cover the entire lateral surface area? Now you have to be careful. This was an equation of the total surface area. What part of this equation is the lateral surface area? Emily?
2 pi r h.
Yeah, the part here at the end, right? The 2 pi r h is the lateral area. So if you imagine a soup can and you were cutting the label off of it, right? The label would just go around the can. It wouldn't be the top and the bottom of the can. Now, if we had the same question, but instead it was asking us about the metal that makes up the top, bottom, and all the way around, that'd be a total surface area. But this is just the lateral area because that's the way the object is described. So we just need I'll call it LA since we're talking about lateral area. The lateral area, which is 2 pi r and h. Okay. They give us h. What is h in our equation? 4. That's right. I'm going to put it over here because I'm going to need a little bit more space. What is r? Half the diameter, exactly right. So right now, my diameter is 2 5/8. That's not a very nice number. So you have a couple of options. If you wish, you could change that fairly okay into a decimal. It's not the worst decimal ever, okay? It terminates at least, so you could do that if you wish. Another option is that you could turn this back into an improper fraction. If you'll remember, the way that we do that is we multiply here and then we add along the top. So I'm going to do it from that perspective just because sometimes you can't change the fraction into an improper or into a decimal and it actually work. Because if it's not terminating, right, no 3 repeating kind of stuff, we're not turning it into that because we'll have to approximate as we start to work with our calculator. So I'm going to turn it into an improper fraction for the moment. So I have 8 times 2, which is 16, plus 5 is 21. So this is 21/8. And I want half of that for my radius. So half of 21/8 would be 21/8, and I know it's divided by 2, but that's not very friendly. So instead of doing that, I'd rather do 21/8 times 1/2, right? Half of it. And I would simply multiply across the top, multiply across the bottom. So 21/16 is what I'm going to put in right here. And you might notice some things pretty nicely cancel. So in particular, this 16 and this 4 cancel, giving me a 4 in this denominator. And then this 4 and this 2 would cancel, leaving me with a 2 in the denominator. So I still have the 21 and the pi on top, but I have a 2 on bottom. This would be the exact expression, so depending on how the directions ask you. Yes, Emily?
I was just confused. How did you get 2 on the bottom?
I reduced my fraction, right? I looked across the diagonal and I said, hey, look, 16 and 4, I can divide them both by 4. And that's how I got my 4. And then I did the same thing over here. I said that 4 and that 2, I can divide them both by 2.
Oh.
I'm reducing my fractions as I go. You don't have to reduce your fractions as you go. You could just multiply across the top, multiply across the bottom, but eventually you're going to have to reduce it anyway. So it's sometimes nicer to reduce it when it's already in smaller pieces than when it's in a larger value to begin with. All right, so I have 21 pi over 2. That's the exact value. I do have it in inches, so I need that part at least. Let me put that in. Now, more often than not, it doesn't make sense to really leave it in that kind of a form. We're talking about a soup label, right? And if you tell somebody who's creating the soup label that the area needs to be 21 pi over 2, they're probably going to give you a funny look and say, no, really, right? That's not what I meant. So if you want to grab your calculator, you can get a decimal approximation. Please do make sure that you're using the pi in the calculator, not any approximation for it. We're not using 3.14. There is a pi that will be more accurate in the calculator. And if we do 21 pi over 2, and typically speaking, we'll round to 2 decimal places. We have 32.99. Oh, and I left the square off. I'm sorry. That should have said inches squared. I'll get it in there. It is area, so it's in square inches. So if they happen to tell you leave it exact, you can leave it with the pi. Generally speaking, that's not reasonable for a word type problem. Okay, any questions on that one? Okay, we're going to move on to a new figure. Look at pyramids, specifically a right pyramid. So you can see drawn in the picture there that it's a square pyramid, it's the one that's been being drawn, but if you changed it to some other shape in the base, you could see how it would change it. It might look more like a star and so forth. The right-hand side is the net for it if you were to cut along the edges of the pyramid and lie it flat. A few pieces of information. You'll notice you have, in this case, 4 triangles, depending on whether you have a square or a rectangle or, a trapezoid, not trapezoid, I meant to say like a octagon or whatever you have at the bottom will change the number of triangles you have. But you've got a number of triangles around the lateral edges, right? And then you've got the area of the base. So the lateral edges, or not edges, but the lateral faces for this object are the triangle faces. And then you have the base. So as you're looking at this, our surface area is this B, which is my area of the base, just like I had before. Whatever that shape happens to be, it's a two-dimensional shape. Plus, I have a bunch of triangles. So I have 1/2. Let me write this to the side. The area of a triangle is 1/2 base times height, right? So the base of each of my pieces is one of these side lengths, right? That's my base. And if it is a regular shape, which is the ones we're working with for pyramids, they're all the same. And then we have the height of my triangles, and the height of my triangles is this L that's occurring right here. It's a slant height. It's not the height of the pyramid, right? The height of the pyramid would be like right here coming down into the middle. That's not the same height. So we sometimes have to work a bit harder to find the correct height that we're looking for here. So we're looking for a slant height. So 1/2 the base side or whatever we've got. Let me write it as B for the moment. I think that's what I've got in my notes. Yeah, there it is. Sorry, there I didn't see it. That base, and then I have times the height, which is L. And then I have times N. And N is because I have multiple ones of these triangles, and I don't know how many. Here it's a square, so I have 4 sides. So the N here is my number of sides of the base. We're about to fix that to where we don't need that anymore, because if you take the number of sides of the base and you multiply by the length of the base, again, what you get, just like with my prism a minute ago, is you get the perimeter of the base. So I can actually rewrite my surface area formula as the area of the base. I'll identify those here in a moment, plus 1/2 times the perimeter times the slant height. So again, this B is the area of a base, and we only have one in these, the area of the base. The P is the perimeter of the base. And then L, it's identified above, but let me identify it here again as well, is the slant height. It's the height of the triangle piece, not the height of the pyramid. I think this one might be the most complicated one in my opinion, because it's often not super friendly to find the L. They don't always give it to you. Sometimes it's given to you and that's fine, but sometimes they don't. They give you the height of the object instead of the height of the triangle, and that can make for a little bit more of a time-consuming process. Let's see what we have as our example for that, though. All right, so this is a real-world example, like for real world. The basic shape of the Transamerica building in San Francisco is a right square pyramid. It has a height of 260 meters, right, an actual height of that, with a perimeter of 140 meters. And it says that the altitude of each triangular face is 261 meters. Find both the lateral area and the surface area of the Transamerica building. So I have space in there. Nope, I don't. All on this page. Okay, so I have a square pyramid. Just did it. There. That's terrible, but we're going to pretend like it's not. Okay, and it tells me that the height of the actual pyramid, I'll do that one in I'll do that in yellow. Right down to the middle here. Is 260. But it tells me that the altitude of the sides, which is another way of describing the slant height, right here, this piece in orange, that piece is 261. Okay. The last piece of information it told me was about the perimeter, I think. The perimeter is 140. So if we go all the way around the perimeter, right? And we did it in a straight line fashion and so forth, we would get 140 meters. Okay, so there's two pieces of information over here in this equation. There's the base, right? The area of the base. That's the area of that square at the bottom. And then this 1/2 PL, this is the lateral area, right? It's the area of all of the triangles, on the sides. So let's actually find the pieces separately, the area of the base, and the area of the lateral area. We find the lateral area, and then we can add them together to find the total area, surface area. So let's actually start with maybe the hardest part on this one, just because of the information we were given, and find the area of the base. Calls it B. So I have a square on the bottom. The perimeter of the square is 140 meters. So what's the side length? Right? Because I'm supposed to do the side length squared. That's the way I find the area of a square. What's the side length if I have a perimeter of 140? What?
35.
And so how did you get 35?
I divided 140 by 4.
Correct. So this right here being the sum of 140, if I take 140 divided by 4, that's a side length. Does that make sense? All the sides have to be the same. There's 4 sides, so we can divide by 4. And you're exactly right, Julie. That's going to give me 35. So this is 35 squared. So what do you get for your area of your base? Did anybody get it? I saw people punching things in calculators. What'd you get? What do you have, Emily?
I just multiplied right here, but I got 1,225.
Yep, 1,225 will be it. And it's in meters, so this would be meters squared. Let's do the lateral area next. The lateral area here is not too bad because they give us all the pieces. So I should have 1/2 times the perimeter times the slant height. So I have my 1/2, my perimeter is the 140 they gave me, and my slant height's 261. So what will I have if I multiply those out?
I got 18,270.
That's what I have too. Good job. Yeah, 18,270 meters squared. Now, they actually asked us for this quantity, right, as our lateral area. So that's one of our answers. The other thing that they asked us for was the total surface area, which can be found by adding these together. So if we do 1225 and add in the 18,270, then we will end up with 19,495 meters squared for our surface area. Any questions on that one? Okay. I think we're just going to stop right there. The example for the cone we won't have time for, so we'll just start talking about the cone next time. You guys have a great weekend.